Swayam Prabha. Digital India. Educated India.
Hello, let us carry forward our discussions on impulse momentum relation. Today we are going to look at the first moment of the Newton's second law and thereby define a new quantity called the angular momentum. Then we will derive the angular impulse momentum relation, which is the angular impulse versus related to the angular momentum. This relation we will derive and look at conservation of angular momentum. Let us start with Newton's second law then. The rate of change of linear momentum is equal to the force and g is the linear momentum, mass times velocity. Consider this point O in the figure. Consider this fixed point O and the radial vector r to the particle at this instant shown. The particle was having a velocity v as shown by that green vector and a force F as shown by the red vector is acting on the particle. If I take the moment of the second law about this fixed point O, then what happens? Let us see that. Moment of the second law about O, that means I do an r cross on both sides of the second law. This is moment of vector, moment of any vector I can define this way. The arm vector cross the vector whose moment I want to find out. Arm vector is r, arm cross vector is the moment of a vector always. This cannot be reversed because cross product as you know is non-commutative. Therefore, whenever we define moment, it is the arm cross the vector, r cross rate of change of linear momentum on the left hand side and r cross f on the right hand side. Let us see what this is, d dt of r cross g. If you do this cross product, let me just do it. This will get, this is the derivative, time derivative of a product. This is d dt of r cross the linear momentum. This is what I have written. What is dr dt? Dr dt is nothing but the velocity vector. What is g? G is mass times velocity vector. Mass is a scalar quantity. Therefore, g is also in the direction of velocity. Therefore, v cross m v must be equal to 0. Therefore, this cross product is 0. What I am left with is r cross the time derivative of the linear momentum vector, which is what I wanted on the left hand side. Therefore, this r cross dg dt, the rate of change of linear momentum, r cross rate of change of linear momentum can be written as d dt of r cross g minus v cross g, and v cross g is 0. Therefore, r cross rate of change of linear momentum is rate of change of moment of the linear momentum. R cross G is moment of the linear momentum. This is one part of the story, left hand side. Right hand side is plain R cross F, and you know what is R cross F? R cross F is the moment of the force. Therefore, we write d dt of H O is m O. What is H O? H O is the moment of the linear momentum about O. What is m O? Moment of the force about O. Therefore, this H O is a new quantity which we have now obtained by taking the moment of Newton's second law about a point. This is called the moment of linear momentum vector, or also commonly called angular momentum vector. This is also a vector quantity, this is a cross product of two vectors, is a vector angular momentum about O. It is very important now to attach this point about which you have taken the moment. So, this is angular momentum about O, or moment of linear momentum about O. We will use this notation H for angular momentum. Thus, we have this angular momentum, the rate of change of angular momentum is equals to moment about O. Now, if you just integrate, just like for linear momentum we integrate over time, we get the change of angular momentum between two time instants is equal to the integral of the moment about O over this time interval. This is the angular impulse momentum relation. Angular impulse is the right hand side. Angular impulse about O, it is very important to specify about which point. Angular impulse about O is equal to the change of the angular momentum about O. Therefore, it straightforwardly follows that if the moment of force on a particle about a fixed point vanishes, then angular momentum of the particle about that point is conserved. The straightforward conclusion. Let us look at this example. This says a small 0.1 kilogram particle is given a velocity of 2 meter per second on the horizontal xy plane and is guided by the fixed curved rail. Friction is negligible. As the particle crosses the y axis at A, its velocity is in the x direction. Notice that this is x direction, therefore, the velocity is in the x direction at this point A. And as it crosses the x axis at B, its velocity makes a 60-degree angle with the x axis. This has been shown in the figure. The radius of curvature of the path at B is 500 millimeter. Determine the time rate of change of angular momentum h o, which means h about O, of the particle about the z axis through O at both A and B. This problem is from the book of Merriam and Craig. We start by writing the angular momentum and angular impulse angular momentum relation that we have just now derived. Rate of change of angular momentum about O is the moment of all forces acting on the particle about O, moment of all forces acting on the particle about O, which is m O. At A, the force acting on the particle comes only in the y axis direction. Here the particle is moving in this direction, the force, so this is the direction of velocity, I will use a different color maybe. This is the velocity and the force that acts from the wall, from the rail, is in the negative y direction. That is why we write F A is equals to minus F A is the magnitude and J is the direction, minus J is the direction. And this implies that the moment of this force about O, which is O A cross F A vector, is equal to 0, straightforward. In other words, at A there is no change of angular momentum about A, the rate of change of angular momentum about A is 0. At B, F B is equal to mass times acceleration of B. Now, how do we represent acceleration? The path curvature has been provided. The radius of curvature of the path is 500 millimeter, whereas this tangential acceleration is 0. There is no force acting in the tangential direction, there is no friction, etc. So, there is no force in the tangential direction, tangential to the path of the particle. I have used that tangent normal coordinate system to represent this acceleration. Therefore, we have only the acceleration along the normal, which is v velocity at B square by radius of curvature of the path. Now, by energy conservation, there is no friction, etc. So, energy is conserved. Therefore, the speed at A must be equal to the speed at B, or speed at B is equal to the speed at A, which is 2 meter per second. Therefore, I can calculate what is the acceleration at B. Acceleration at B is equal to this V B square by rho B in the direction of E n cap. Direction of E n cap can be easily found. This angle, this is E n cap, this angle is 60 degree. So, tangent makes 60 degree, therefore, this must be 30 degree. Therefore, E n cap vector in the x y z coordinate system can be represented as minus cosine 30 I cap minus sine 30 j cap. Radius of curvature is 0.5 meter specified. Therefore, acceleration at point B is mass times the so acceleration at point B is given by this expression, that is acceleration at point B, and the force at point B can be then found out as mass times that acceleration of point B, acceleration at point B. Mass is 0.1 kilogram, that gives us the force F B vector, which I have written out. And from here I can calculate the moment of this force about O, which is O B, this is the arm, cross the force at B, and if you do that cross product, O B is 0.3 I cap, that is O B. Therefore, 0.3 I cap cross F B, I cross I is 0, I cross j is k, and therefore, it is minus 0.12 k Newton meter. This is moment, and this must be equal to rate of change of angular momentum about O of the particle at B. Therefore, H about O at the location B, H dot about O at the location B is minus 0.12 k cap kg meter square per second square. Now, here I would like to point out that the units of this is rate of change of angular momentum about O, rate of change of angular momentum about O. This is moment, Newton meter, and that is equal to the rate of change of angular momentum. Now, I have written therefore, rate of change of angular momentum has units of Newton meter, and Newton meter is kg meter per second square is Newton times meter, which is kg meter square per second square. Therefore, H O dot has this units of kg meter square per second square. H O, which is moment of linear momentum, therefore, will have units. So, R is meter times this is linear momentum mass into velocity. Therefore, the units of H naught, which is the moment of linear momentum, is kg meter square per second. And if you look at the impulse momentum form, which says that change of angular momentum is integral of the moment about O. This is after I do that integration over time. This is the angular impulse momentum form. From here also you can find units of angular momentum, which is Newton meter is the unit of moment and second is unit of time. When you integrate, so it is moment times time. Therefore, H also has this unit Newton meter second, which you can now you can change Newton to kg meters per second square and get the same unit. Therefore, you can find this angular momentum being expressed in various kinds of units. Let us go over to the next problem. The bob of a pendulum is released from theta equal to theta naught. The bob of a pendulum released from theta equal to theta naught, you can see in the figure, hits the frictionless ground and moves straight till the string becomes taut again and lifts up to theta equal to theta 1. So, this is a pendulum which is hung from a point, and there is a floor or ground which is less, which so the point of hanging is at h, which is less than L. Here h is less than the length of the pendulum, then it will hit the ground. Now, this ground is frictionless, and once this bob hits the ground, here we are making assumption that it moves in a straight line, it does not bounce off, it is not like a ball which bounces off. Okay. So, which means some part of the energy has been absorbed by the ground, or once again I will talk about linear momentum in a minute. Okay. The bob hits the ground, moves horizontally straight on the frictionless ground, and here when the string again becomes taut, it again moves in a curve, lifts up, but now up to theta 1. Taking the length of the pendulum to be L and height of the support to be h, which is of course less than L, determine theta 1 in terms of the other parameters. Now, when it hits the ground, let us call that point A, as I have marked in the figure. The ground being frictionless, there is no horizontal force. Therefore, the linear momentum in the horizontal direction must be conserved, but there is a vertical impulse. What has happened? If you notice carefully, the bob was travelling on an arc, hits the ground, at that just before it hits the ground its velocity was V a minus. Just after it has hit the ground its velocity is V a plus. These two directions are different, you can notice these two directions are different and this happens almost instantaneously. Therefore, there must be an impulse. In which direction this change has taken place? In the vertical direction. So, there must have been an impulse in the vertical direction. In the horizontal direction there is momentum conservation, there is no force in the horizontal direction. Conserving linear momentum in the horizontal direction, I can write this mass times V a minus, this is the green vector, cos phi is the horizontal component. You can check that if this angle is phi as marked, then this angle is also phi. Therefore, mass times V a minus cos phi is equal to V a mass times velocity of a just after the impulse, because after the impulse it is horizontal only. V a plus is horizontal, and I can calculate cos phi as h over L, straightforward geometry. Now, this moves on frictionless ground, therefore, its velocity will be maintained. What will happen? This it has from V a minus it has gone to V a plus, and now it will move with this velocity V a plus. Therefore, V b minus, which is just before the string gets taut, this velocity V b minus must be equal to V a plus. This velocity V a minus just before the string gets taut, this velocity V b minus is must be equal to V a plus. Okay. Now, how do I calculate here V a minus? The question is, how do I calculate here V a minus? Because if I know V a minus, I can calculate V a plus from here. But what about V a minus? For that, I conserve energy from this state to this state. The bob of the pendulum starting from theta naught to reaching this angle phi. So, that part is a free motion means it is only under gravity, and gravity is a potential force, therefore, energy will be conserved. There is no other force which is doing work. Tension is definitely there, but tension is perpendicular to the direction of motion. Therefore, the tension force of the string will not do any work. This is an example where the force being perpendicular to the path does not do any work. Therefore, it is only the total mechanical energy will be conserved. The final kinetic energy, the potential, I am taking potential datum as the ground, the horizontal. Therefore, there the potential is 0, the kinetic energy is half mass times velocity a minus whole square, and when it started off from theta naught it was released. Therefore, the initial velocity or the initial kinetic energy is 0, it is only potential energy. How much is the potential energy? mg times h minus L cosine theta naught. This is straightforward geometry which you can calculate. Here I have marked this distance is h minus L cosine theta naught. Therefore, mg, and that is the datum, from datum I am measuring it. Therefore, I have mg h minus L cos theta naught as the potential energy with which it started off, 0 kinetic energy, and that is converted to kinetic energy and 0 potential energy. So, kinetic energy I can find out, therefore, V m minus I can find out. Therefore, V m minus is this. and V A plus, therefore, I can find from that conservation of linear momentum in the horizontal direction. And as I just now mentioned that V A plus will also be equal to V B minus. Before the string gets taut, this velocity will remain the same because it is sliding on a frictionless ground. Let us carry forward at B. Now, at B the string suddenly gets taut, and this suddenly getting taut gives an impulsive force because of the string tension, and as a result you will notice that the velocity direction suddenly has changed. It was moving in a horizontal, straight horizontal path. Suddenly it has taken a velocity which is tangential to an arc of a circle. Therefore, there is a sudden change in the direction of velocity vector. V B minus goes to V B plus almost instantaneously. Who is responsible for this change in direction? Some impulsive force, and what is the impulsive force that acts? String, the string tension. The string tension suddenly gives an impulsive force and changes the linear momentum direction or the velocity direction. Now, this is an impulsive force, but this force is acting through that point O. Remember, this impulsive force, which may have very high magnitude, is acting through this point O. Therefore, the moment of this impulsive force about O is 0. The moment of the force, the impulsive force in the string that is generated in the string at B, the moment of that force about O is 0, because the string gets taut and BO is that straight line along which the string tension acts. Therefore, the string tension, the impulsive string tension acts through O. Therefore, the moment of that force, the tension force, impulsive tension force is 0 about O, which means what? The angular momentum or the moment of linear momentum of the bob about O must be conserved. The angular momentum or the moment of linear momentum of the bob about O must be 0. Therefore, let us try to calculate the angular momentum about O. Just before the string gets taut, the angular momentum about O, this is the velocity. So, mass times velocity m v b minus, this is the linear momentum. Moment of linear momentum about O, therefore, must be the perpendicular distance from O to the line of velocity, and that perpendicular distance is h. Therefore, h times m v b minus is the moment of linear momentum about O. That is the left hand side. Right hand side, this velocity V B plus, which is just after the impulsive force has acted, this is moving in an arc just like as a pendulum does. Therefore, this velocity must be perpendicular to the string. Linear momentum just after the impulsive force has acted is m v b plus, and moment of linear momentum is the perpendicular distance from this, and that is equal to L. Therefore, that is the moment of linear momentum just after the impulse, and just before the impulse it is h times m v b minus. These two things done, it is straightforward to determine V B plus. Mass cancels out. So, for V B plus is h by L, V B minus, and V B minus remember is V A plus, which we have just now derived, and I have written out the expression for V B minus. You can find out V B plus. Now, what do we do with V B plus? Again use energy conservation. The Bob moves under gravitational force, the tension after this, after the impulsive force has gone out, it is only the string tension which acts perpendicular to the direction of motion or path of the particle. Therefore, it will not do any work. Only thing that does work is gravity, the weight, and that is the potential force. I can use energy conservation. So, the total mechanical energy will be conserved. At the initial point at B, it is only kinetic energy, potential energy is 0. Remember, the datum is that horizontal line. So, it is only kinetic energy must be equal to the total mechanical energy at the highest point, where it is only potential energy, no kinetic energy, and the potential at the highest point is mg h minus L cosine theta 1. It moves up to an angle theta 1. If you do these calculations, if you substitute the expression of V b minus here and calculate V b plus, substitute that V b plus here, and finally do simplifying cancellations on both sides, you will get this relation. This is straightforward algebra, you can do it and check how theta 1 is related to the other parameters. Cosine of theta 1 expression you can find out easily. This is in terms of h, L, theta naught, etc. So, this problem shows the application of linear momentum conservation, angular momentum conservation, presence of impulsive forces, and how they do not contribute to in over that very short duration, they do not contribute to the change in linear or angular momenta. So, all these concepts have been used in this problem. So, to summarize, we started off by taking the first moment of Newton's second law and defined a quantity called angular momentum, which is the moment of linear momentum. This angular momentum equation once again is a vector equation. Then by integrating over time, we obtained the angular impulse momentum relation. Under certain situations where the moment is 0, we have obtained moment of the force acting on the particle is 0 about a certain point, then the angular momentum is conserved, and we have looked at some applications of this concept. So, with that I will close this lecture.